let's just have a look. So over here, I'm just only using this for illustrative purposes. I don't endorse any of these companies. So these are just some of the services that most of you are familiar with and you've come to rely on. And so let's talk about how we got from the diagram you saw on the left, which was just only 4 nodes and a concept, into now what you saw in the previous slide with all those service providers that are now giving you essential services. So let's go back to the 1950s. So everything at this time, the world was very, very different from what we have today. So one of the things is that that time, Kenya was not yet independent. That's a fact. This time there were 2 major superpowers, the United States and the Soviet Union. They were actually escalating the Cold War. Both of them were testing nuclear weapons. On the left-hand side, I have a picture of a nuclear test that was done in the Pacific, known as the Bikini Atoll. It's today's Marshall Islands. This was performed by the United States. However, in 1957, things started be to go a notch higher. The Soviet Union launched Sputnik 1, which is a satellite. And in the United States, because of this fierce competition between these 2 superpowers, there was a panic. And people thought that next the Soviet Union will be able to launch nuclear weapons from space. So in 1958, the then United States President, Dwight D. Eisenhower, the 34th President of the US, he launched a research arm in the Pentagon known as the Advanced Research Project Agency. ARPA would actually play a very, very critical role in actually developing the internet and the internet protocols that we've come to rely on. And at the same time, ARPA was developed to actually make technological breakthroughs. You could call them almost in the realm of science fiction, such that the United States will never actually be surprised again by maybe an advancement like what you saw in Sputnik. So this is where things become interesting because around 1961, Leonard Kleinrock, who was then a PhD student at MIT, he came up with a very interesting concept of sending messages through what you call packets. Although the term packet wasn't yet used then, that will come much later. And in his PhD thesis, he was thinking of a way that you could send information in a way that is different from how the telephone system used to work, which used to rely on circuit switching. However, the very idea of even the internet, or even how it was visualized as how we see today, was actually brought by a visionary by the name Joseph Carl Robnett, or JCR Licklider. Licklider wrote a concept known as the intergalactic network. So in the intergalactic network, he thought of a network where everyone could connect to any service, can share it, and it is actually global, not even just only global. He was thinking it could also connect even distant planets and galaxies. So this was a thought at that time, how you can actually maybe have a network that is so universal that anybody can access it. And this was in 1962, which is nearly 60 years ago. So now that we've brought about, so the idea that sounds now science fiction, so how did it actually become to be realized, to become actual science, to become actual engineering? So first and foremost, between 1965 to 1968, some fascinating experiments were conducted. One was conducted between Larry Roberts, whom you see on the left-hand side, and Thomas Merrill, who was also working with him, to connect just 2 computers, one in MIT and the other one in Santa Monica, over just a very, 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 today it's very slow, but in that time it was a state-of-the-art technology, a 2.4 kilobit per second telephone line. They actually showed that those computers can actually talk if over a phone line, but then the more appropriate method of actually exchanging data will not be using the phone line per se, but using a concept that actually came to be known as packet switching. And this concept was actually introduced in 1967, but not by one person, but by 3 teams that were working differently. They had not even met one another. So in the first ACM symposium on operating system concepts, Larry Roberts, who was at ARPA, Paul Baran, who was at the RAND Corporation, and Donald Davis and Roger Scantlebury, who are at the National Physical Laboratory in the United Kingdom. Each of them independently were working on an idea, and when they actually compared notes, they found that they're working all on the same idea. And this then came to be known as packet switching, and the name packet started to actually be coined in 1967. All right then. So now that the idea of packet switching could demonstratively be put in practice, in 1969 is where we find the birth of the precursor of the internet, which is known as the ARPANET, which was the Advanced Research Project Agency Network. So the idea was to connect at least the 4 nodes. So this was similar to the diagram I'd shown much earlier on. And the 4 nodes were in the University of California, Los Angeles, the Stanford Research Institute, University of California, Santa Barbara, and the University of Utah. So all these 4 networks were connected via to one another, of course, using the technology at that time. But this time they're going to implement packet switch networks. So, on October 29th, the ARPANET was tested for the first time around 9 p.m. And if you see on the right-hand side, these are the notes taken by Leonard Kleinrock, who actually sent a message from the UCLA to SRI. And in the message, he wrote the first message. It is login. So he sent the L, and then he sent the O, and then then after that, the network crashed. But then he actually retried again, sending now the full message login, and this time it worked. Leonard Kleinrock, 3 years ago in a video I saw on YouTube, he said that he was very happy that at least he knew that it could work, even though it had crashed. He just wanted to prove that it could actually work, and it actually did. And this was the birth of actually a revolution, which would actually shape even our world. So also in 1969, a very important document known as the Request for Comments was actually drafted. The first one was drafted by Steve Crocker, who is an internet pioneer and who served at the ICANN board until 2016. And in this, I've taken a snippet of the first RFC. It was drafted on the 7th of April, and it was on host software. So today, I will have to say that RFCs are still used today. They are sort of the de facto technical laws or network internet laws, and they are maintained by the Internet Engineering Task Force. And you'll come to actually see some of the RFCs. I'll mention some of them that will actually define some of the most important technologies that we are now currently dependent on. In the 1970s, now ARPANET started to actually take, let's say it went on a roll. So in 1970, from four machines, now there are 9 machines that were connected. In 1972, email was designed by Ray Tomlinson. In 1974, a new revolution came up, and this was actually led by 2 DARPA scientists, Robert Kahn and Vinton Cerf, who had actually borrowed a concept from a French computer scientist known as Louis Pouzin. In it, they describe basically a protocol which should be able to connect different computers on separate kind of networks. So when I say separate networks, we're talking of different technologies. So whether the computer is connected to a radio network, a phone line, fiber, Wi-Fi, they should actually all talk the same protocol, or they should talk the same language, in other words. This protocol came to actually be a core ingredient to the success of the internet because we still even use it today. This was known as the Transmission Control Protocol, and it was specified in a document known as RFC 675. And I've said it's actually still used today, and it is still powered what we have as our internet. In 1978, it was the first spam email. And in this case here, there was a company which is now defunct called the Digital Equipment Corporation. And they were selling, or they're advertising a DEC system 2020. Interesting that they mentioned it after on the year in the year 2020. Okay, I just make a link between the two. So they are trying to actually showcase their product and via an email, and this was the first spam message. Okay, so now we go to the 80s. So in this decade, very many breakthroughs happened and very many things started to occur that actually were dazzling in their own right. So in 1980 now, there were 200 computers that were connected to ARPANET. I should mention that right now we have not come to the term internet. All this is still being done in the ARPANET, which is basically military network, and it is built by engineers. And all these engineers are a tightly knit group and they know one another. And in 1983, ARPANET starts to deploy now the new protocol, TCP/IP. DNS, which is actually the domain name service, was actually invented in 1983 by John Postel, whom you see on your left, and Paul Makapatis also, who you see on the center left, both of whom were actually trying to solve a problem whereby how to create, let's say, a phone directory or of course, without actually sending a huge file or called the host file, which was not actually quite scalable. But at the same time, I also want to take a particular mention to also women pioneers, because there are very many women pioneers who actually contributed also greatly to the advancement of the internet and also of computing as a whole. One of whom is Radia Perlman. She is actually an inductee of the Internet Hall of Fame. She designed an algorithm and a protocol known as spanning tree protocol. The STP actually helps networks in self-healing, and without it, we'll have many, many errors, especially when you're talking of network bridges. There'll be errors and we'll actually have a network that is a pain to use. So she contributed quite a lot in helping in the resiliency of actually networks, especially on the layer 2. In 1986, the Internet Engineering Task Force is formed, and the ITF makes the standards and maintains the RFCs like that I mentioned earlier. 1989, a new revolution occurred. The web was actually invented by Tim Berners-Lee, whom you see on your right. At the same time, the first commercial ISP, it was known as the World, actually went online. And at the same time, the Cold War ends, and the crazy nuclear race between the United States and the Soviet Union, although still there are still nuclear weapons in both countries today, though in Russian, but not the Soviet Union. But the Cold War officially ends in 1989. And now we come to the 90s. So the 90s is where now we see the ARPANET actually finally closes and it gives way to actually becoming the internet. So various things happened in the 90s, one of which is the first commercial internet exchange point, which is actually called Commercial Internet Exchange Point, is formed in Virginia, 1991. In 1991, the first website, the first web browser released by Tim Berners-Lee. So at this time, there's only one website and maybe just a couple or dozen users at CERN. This was this was going to change drastically. In 1993, the first graphical web browser is developed at the University of Illinois Urbana-Champaign. And then in 1995, we see a burst, can I say a boom? 23,500 websites are actually designed and 16 million internet users actually go online. And we have sites like Amazon, AuctionWeb, Alta Vista. Okay, Amazon has survived, it's still survived. The rest actually are no longer there, they are now defunct. 1995, also at the same time, a very important protocol which is used in routing and which actually forms the basis of routing today is actually defined. It's known as the Border Gateway Protocol. It was later standardized in RFC 1883. In 98, the organization I work for is founded, ICANN. This time now the web has exploded to 2.4 million websites. Surprisingly, Google is also founded in the same month as ICANN on September 1998. And this time globally, there were 88 million internet users. In 1999, at the end of the millennium, we have 3.1 million websites, and PayPal is founded at this time. The number of users grows from 188 to 281 million users. Okay, so over here, just to show you a visual, this is how Google looked like in 1997, 1998. It was hosted on the Stanford servers. It was even, its domain name was even google.stanford.edu. So it hadn't even had, because at this time it was a PhD project, but We know that the PhD project became actually one of the most important websites in the entire world. And you had other sites like Yahoo. It's just an illustration of how Yahoo looked like, and also eBay. So this is the 90s. So that's that. All right, so we come to the 2000s and up to today. So this period, we'll say, is defined by the rise of social media. So in 2001, Wikipedia goes online and the number of websites is nearly 30 million, but 500 million internet users. In 2003, LinkedIn and WordPress actually are established, and now you have 778 million internet users and 40.9 million websites. Facebook actually goes online in 2004, and we are now approaching 1 billion users. But the 1 billion user mark is crossed in 2005 when YouTube goes online and the number of websites mushrooms to 64.8 million. 2006, now we have 1.16 billion internet users. Twitter goes online and there are 85 million websites. By 2010, we've crossed now the 2 billion internet users. And Pinterest is established, and we have now 207, nearly 207 million websites. In 2015, the 3 billion mark is crossed with 863 million websites. In 2017, now the 4 billion mark is crossed. And we have now even the 1 billion websites, more than 1 billion websites. So there are now nearly 1.8 billion websites. As of yesterday, the internet contains a total of 98,742 networks. So networks are basically handled by institutions such as maybe ICANN has its own network, Wananchi Online, Safaricom, Google, Facebook. All these are networks that connect billions of people to, and also billions of websites together. So now we're approaching 100,000 autonomous systems networks, and the threshold is now over 4.7 billion. And so, giving now this brief history, we should ask ourselves some very interesting questions. Why do you think the internet achieved such phenomenal growth? What led to this? Were there some deliberate, can I call it mindsets, apart from the fact that there was a great vision from a science fiction concept of an intergalactic network? So the idea, and this has been documented, is that the internet's success can be basically summed up in three principles. One of them is end-to-end principles. So when the ARPANET went online in 1969, the designers thought of actually creating a network whereby the intelligence that is on the nodes. So it is actually on the nodes that you can actually perform very complex tasks, such as maybe browsing a website, checking an email, performing complex operations. But between the nodes, that is in the network, there should be no intelligence. The network should just basically send packets and receive packets. It should not in any way do anything except to send and receive packets. This actually made it a very simple way of actually designing a network, because you don't have to think of complex, very, very complex protocols or complex software to put in the network. You just only worry about actually doing that on the endpoints, which is basically the computers or the mobile phones. Those are the ones that actually should be smart. The second one is on openness. One of the things that I've come to really appreciate, because in my career, I've actually come to meet some of the visionaries who made the internet, like Vinton Cerf and Bob Kahn. They were here in Nairobi in 2011 during the Internet Governance Forum. And one of the key principles they made is that the internet has to have open standards, and it should actually be built using open source software. The open source software is actually a movement in its own that has helped shape the internet. And without having an open standard whereby you and I or anybody can actually join an institution like the IETF or even ICANN, where you can actually contribute to policy or to even the technical standards themselves, the internet will not have actually seen the level of success that we've seen today. So openness and allowing actually end users, anybody from anywhere in the world, regardless of their background, to actually participate on the internet through contributing to standards or to software was actually a very, very important principle that helped shape the success of the internet. And then lastly was access. So one of the things that was one of the key design goals is that if I have perhaps say a service in say in the United States, there should be no difference in how I actually view or interact with that service, whether I'm in Kenya, maybe whether I'm in Belarus, maybe I'm in Japan, or even in, let's say, Germany. The same service should be accessed anywhere in the world from a single point of perspective. You would say from a single perspective. So in this way, the idea that basically anybody should be able to access that service, and at the same time, the internet was built in a way such that it is totally decentralized. There's no one party, one entity, one government, one corporation that controls the internet. The internet is multiple organizations, multiple individuals who actually have volunteered to connect each other's networks together and share data, share services, and also to create now what you call the network of networks. This design principles is what has led and shaped the internet from the concept that was introduced in the 60s to now the phenomenal network that we've come to rely on. And one of the two technologies that actually define and underpin how the internet works and are based on the guiding principles is routing. So based on these design principles, routing came about from the fact that networks owned by organizations should be able to send packets to one another using perhaps certain matrices, maybe like the shortest path from one part of the internet to the other, or maybe based on cost. So this is just an example, and I was using the Deutsche Telekom, but it can be any organization. So if I wanted to send from Deutsche Telekom to ICANN a packet, so a route is created, but since Deutsche Telekom does not connect directly to ICANN, it has to form what you call associations or peering agreements with various network providers in between. And based on those agreements, they are now able to actually send packets. And like I mentioned earlier, the Border Gateway Protocol, which was introduced in 1995, is actually used in actually peering and actually connecting all these various network entities together in order to send packets via various routes. And that is just an illustration of one of the protocols that was based and designed based on those guiding principles. The other one is actually DNS, which is basically what we at ICANN eat, sleep, and drink. And DNS is a protocol that is so essential today, just as routing is, because without it, we'll not be able to reach the services that we are actually accustomed to. So DNS is like the yellow pages of the phone directory of the internet. If I want to actually go to WhatsApp from my device, the first thing I do is actually send the query of whatsapp.com to my ISP or recursive resolver, which is the diagram you see on the center. From the ISP, the resolver now checks, and if it sees that it has a record of the domain name and the IP address, it returns to my device. Otherwise, it goes through a process of contacting various servers. The first one it contacts is the root server, which is maintained by 12 operators. And the root tells it that basically I don't know whatsapp.com, but I do know the .com service. I know where .com is, so it gives a referral to the recursive resolver in the ISP. The ISP server then contacts the .com service, tells it that I do know where whatsapp.com is. It gives it a referral, and it then checks out the whatsapp.com, which is based in Facebook network. and then it returns the correct IP address, and then you're able to connect now from your phone to the WhatsApp, let's say, app, and do the operations that you wanted to do. So this is just an illustration of how DNS works. And so given that we have just talked of the two essential, most important protocols that actually glue together all these entities, from the networks to the applications to devices, I'd like to talk about quickly and say that despite even all the phenomenal growth and also the fact that the internet is so key to our lives, there are very, very major challenges that the internet still faces today. Security is a big challenge, and I also foresee it's still going to be a challenge going forward into the future. One of the problems is that when the internet was created, it was created with trust in mind. So everyone trusted one another. Vint Cerf trusted Bob Kahn, trusted Ray Tomlinson, who trusted Jonathan Postel at the Openness. So security was not really considered or built on the internet. What was most important was actually access, and actually to actually see that the project of the network of networks actually successful. But given the challenges of malware, of surveillance, man-in-the-middle attacks, spam, phishing, this, and also now the growth of IoT, which will add by 2025, over 20 billion devices that will now rely on the internet will go online. This has actually made security actually a topic of high interest, and both in the technical and in the policy communities. And it's still going to be a topic that is still being addressed, and it will continue to be addressed going forward. The other one is privacy and data protection. The fact that you have the growth of, can I call it, big tech companies, and also certain governments where they themselves collect your data without maybe your knowledge, without your consent, and you're not sure what they do with that data, is actually a big challenge because, and this is something that is also of interest, not just only to end users, but across governments. We are seeing it, especially when the European Union introduced the GDRP, and so privacy and data protection will still also feature. And problems also and challenges that are also being faced is the internet shutdowns, which actually severely disrupt the net. It's not just, it can disrupt essential services, can also disrupt also our country's economy. We're also seeing surveillance. I'll not mention about what Edward Snowden revealed, but he showed that basically the internet has become such an interesting medium that can be used to easily surveil and find out about maybe and track people's activities and other things. And there's also the issue of fragmentation. We are seeing various measures by also, especially certain states, they have their own reasons for doing so. But mainly it's because of political expediency that now some states want to actually create separate network that is, let's say, independent of now the public internet. And so that's just one of the issues that we are seeing. And another one is that there are certain also institutions and individuals that actually are completely or don't agree with the design principles. They feel perhaps it is more essential that protocols are not built in an open manner, but in a closed, secluded manner. Again, they have their reasons for that, but as you can see, these challenges actually bring a lot of pressure on a more open and also more universal internet. And and I see that even going forward, that these issues will actually feature more and more. And this brings me to my final slide. I just want to show you perhaps maybe some certain future scenarios. So on my left-hand side, we could end up actually building a network that is accessible by machines with intelligence that may decide to actually get rid of their human overlords. It's just one possible scenario, but maybe this could be in the realm of science fiction, but I am not so sure. But hopefully, I hope not. But on the right-hand side, we could see basically as we get more and more interconnected, we may find that even when it comes to maybe our physiology or even our bodies, we may want to actually augment them with digital devices, and we also with the internet. So we may see more and more, let's say, innovations and inventions in the fields of implants, of nanotechnology that not just only connect us to the internet, but also connect certain bodily functions, cells, and even certain parts of you to the network itself. There are experiments that are currently taking place. Other than that, there are also possibilities of as we go forward in the future, is that we may see also greater onslaught on privacy, as I've mentioned. We may also see at the same time also new innovations that can drastically alter even our perception of reality. We've already seen how fake news on social media is actually affecting our perception on what is real and what is false. Just imagine now if you could actually have near, can I call it, near convincing illusions, maybe brought about by virtual reality, that actually creates an alternate, maybe universe from what we're used to. These are certain possibilities that may actually come in the not too far away distant future. And also, other than that, we are also seeing new innovations in IoT. We are seeing innovations in quantum computing, which will basically render some of our security and algorithms and protocols that we currently use obsolete by then. So these are just some of the possible futures, but well, I hope I hope that basically the internet will continue to actually play a more positive role in our world, and let's just hope and see. Let's just wait and see. So with that, I just want to come to the end of my presentation. And if you like to reach us out at ICANN, you can check out our website, follow us on Twitter, or you can go to our Facebook page, YouTube, and all the social media links. So thank you so much for listening, and I'll be happy to take your questions. Okay,
Hi,
so
Paul. There are some questions on the chat.
yes. All right, so
Yes,
so
you
I'm
will just
read
go through them.
So, you asked a question on how some engineers or developers oppose guiding principles. Right. So okay, one of it is actually unintentional. Let me say, like the end-to-end principle has been violated in many ways, not in any bad way, but what has violated the end-to-end principle is middle boxes. So middle boxes are devices like routers, switches, or even firewalls that basically perform other functions that between now the endpoints. So for example, a middle box basically can, if you're sending a packet from let's say point A to point B. So the middle box may see the packet and then it strips it of certain headers, certain features, and in that way you violate the end-to-end principle. So it is actually, you could say middle boxes are unnecessary evil. They came about because of certain limitations with initially with the initial protocols, one of which was on security, as I mentioned, so firewalls. The other one was actually also on addressing. So when the ARPANET was designed in 1983, they only had 4.3 billion IPv4 addresses. And then now, of course, given what you see, the scenario is where we have over 4.7 billion internet users. So in this case here, you find that there needed to be a new protocol, which is IPv6, which was actually designed and specified in 1998. However, between 1983 and 1998, in order to go around this limitation, the engineers, they built what you call network attack, NAT, which is basically creates private IP addresses. So you could actually have one IP before, but then behind it you have all this 192.168.1. So on 10.10.10. This is actually NAT, which came into the picture, and NAT actually compromised in a way the end-to-end principle. Then, all right, so Megan, thank you for your question. What is the future internet from technical perspective? Okay, the Clean Network program was actually initiated by President Donald Trump through his also Secretary of State Pompeo. And so what Trump actually is making and he's trying is actually more of a political decision that has technical implications. So in his policy, he wants basically American companies not to deal directly with Chinese corporations such as Huawei, and therefore this is based on a it's 12 hours political consideration. In this case here, what this could lead to, although it has not yet been implemented, is maybe you may find that corporations in America may be forced to route their traffic around China. They could maybe take their traffic to maybe say Europe first, away from as long as it does not go through any Chinese networks. This has a very, very negative impact in my view. This is my personal view as Paul, not as ICANN staff. In my view, because what you're actually doing is that you're creating two separate uh, types of networks. So there's what you call, which is one that is the US centric one, and perhaps one maybe that could be Chinese centric. And each of them will have maybe different protocols for interconnecting one another. You may find that BGP, or the routing protocol I described earlier, will be compromised such that you'll filter certain routes. You'll see that all these routes that are going to this destination, and this destination is through China, filter them out. And this has very negative impact also on a technical level. So this is an example of the splinter net. Yeah, and I agree with you. Yes, the Clean Network program in a way is actually an example of what could happen if political considerations, notwithstanding, actually applied, and they have themselves technical consequences. Okay, kindly comment on Internet Society and our membership as a country who controls the internet. And okay, so basically, and it's every country okay. Okay, all right. So Abdi Rahman, let me just take you to the slide with my contacts. Okay, all right. So I'll start with the least one. That's the slide with icon contacts. All right. I'm not. I mean, I don't have the authority or competency to comment about the Internet Society. All I'll just mention is that the Internet Society actually plays a very key role in technical leadership and also advancing the internet in terms of building IXPs, and also in routing. They have a project called Manners, which is to ensure basically that organizations that manage their networks are able to secure their routing and from hijacking. But since I'm not a member, I'll not comment on the Internet Society. And let me say who controls the internet. Okay, so the internet doesn't have a single point of control. The internet is a very decentralized network of networks. And what happens is that each network, which is maybe run by an organization, an end user, and so on, all these 98,000 networks, they voluntarily agree on norms and on technical norms, which are called protocols, to interconnect with one another, to send traffic to each other, to actually perform certain operations and provide certain services within these technical norms. And all these technical norms are defined in various organizations, such as the W3C, which was created by Tim Berners-Lee, by the IETF, the Internet Engineering Task Force, and also by the likes of the IEEE, which now is built now hardware devices, and of course, the open source software community. So you have all these participants from government, private sector, individuals, civil society, all of them voluntarily agreeing that this is how we like to operate technically, and so on. So the biggest point of contention is more or less on the policy aspect. So when it comes to issues like net neutrality, whether maybe certain network operators can slow down traffic, or when it comes to issues like cybersecurity, this is where things become very murky and very tricky because each of these participants have different views and perspective of how best all of these policy issues should be addressed. Although I'm not going to talk about this right now because I'm not a policy expert in this, but when it comes to policy, there are very different views. There are very different ways of which participants and even stakeholders have viewed things. In ICANN itself, which deals with now the DNS, you have various constituencies, each of which has various needs, and each of them tries to address those needs in terms of how ICANN should actually handle maybe or tackle a certain issue with respect to DNS, such as DNS abuse, through now the multi-stakeholder process. The other multi-stakeholder process is the Internet Governance Forum, which now has treats many other issues uh, beyond even what ICANN can handle. And these are just some examples. Now, when it comes to sovereignty, again, I'm not competent in taking this, but I can mention certain things like when you talk of the .ke, which is the country code top level domain for Kenya. So each country in the world has its own country code top level domain and it is sovereign. ICANN, for example, does not tell KENIC or perhaps maybe let's just call it CINIC, which is in China, how to manage that domain. It is completely autonomous, it's totally independent, and it is handled in the best way each country or the members of the stakeholder or even the government regulators in that country best see fit to handle now the country code top level domain. So this is just an example of how I've just shown how sovereignty comes in certain key areas. The other one could be on infrastructure, like the fiber backbone. So certain countries have certain agreements with one another. Some are bilateral, some are multilateral. So there are various issues there. And okay, so I hope that answers your question. All right, so Megan, again, why is the full transition of IPv6 still a problem? Has Kenya relevant stakeholders made a full transition? All right, I will address the first part of the question. May not be able to address the second one because there are various stakeholders in the country who are implementing it, and I do not know their positions on this. So when it comes to IPv6, one of the biggest problems is okay, so in 1998, the protocol that is for IPv6 was defined. And ever since 1998, the progress has been slow because one of the things is that when it comes to implementing it, there is a steep learning curve. IPv6 is very different from IPv4. Its address structure is very different. Its way of actually even configuring is quite different. And then the other thing is that by let's say the early 2000s or even up to 2015 or 2012, that time when we had the first IPv6 day, you find that many organizations, institutions have already had core routers, core infrastructure that was configured in IPv4. They had tested it. They had spent quite a considerable amount of investment in actually just setting up that and making sure it works. Now, to transition to IPv6, you now have to tell maybe some of those organizations to buy maybe new vendor equipment to configure it and also to actually test and deploy it. And this is actually not easy. It's actually a very steep learning curve. It also is an investment on the part of the organization that perhaps maybe wants to implement IPv6. So in this case here, IPv6 has been very slow in its uptake. There are certain, well, let's just call it, can I call it initiatives, particularly from the Internet Society. They've been more active in this, in actually getting institutions to turn on their, maybe some of their core infrastructure to actually IPv6. Some have, but even with that, also remember IPv6 also introduces also new challenges. One of them is security challenges, and there's been quite a lot written more on this in the IETF on improving our IPv6 security. So this is why also IPv6 still,
And
I'm happy
hello,
that, hello?
hello. Would you please expound on what IPv6 is for some of us who are interacting with some of these terms for the first time? Thank you.
Okay, all right. So let me just, okay, so I'm very, very, very sorry about this. So let me just bring this concept. So let's go back a little bit.
Attention, Paul. New date. Mental health.
Sorry about that. I usually get alerts. So in the 1980s, when TCP/IP, which I had explained earlier, went online, the protocol then was IP version 4. The version numbers actually were from various experiments. So there was version 1, there was 4, there was even 5, and then there's 6. So IP version 4 defined that you could actually create addresses for up to 4.3 billion machines. So why I'll explain also go down. Machines need addresses because they do not actually understand. They don't understand, let's say, names. They don't understand something like KICTANet.org.ke. So in order for a machine to actually process data, they're defined or they're referred to as addresses, similar to a phone. So your phone, you actually contact it using a phone number. You don't actually contact someone maybe using maybe some string or some word. You usually use a number. Similarly, machines actually, they address them using a number. So IPv4 was created and it supported up to 4.3 billion machines. However, by the 90s, it was discovered that 4.3 billion will not be enough because the internet was growing at an exponential pace. So engineers, one of it, also the Internet Society contributed a lot to this. They created a new addressing scheme called IPv6. IPv6 is actually defined in RFC 2410. I'll check it out. I will share it with you after this. And in it, it proposes a new addressing scheme. So in this addressing scheme, you can actually support billions and billions of devices, even trillions. It's actually a very huge. It is actually, let me give the number. It is the number 2 followed by 36 zeros. So that's even more than a trillion. It's even more than a billion. And IPv6 is now the standard that is currently being deployed in various organizations and even by various service providers, including some of the whom I had shown earlier on. And IPv6 is actually supposed to be a successor to IPv4. However, as I've explained to Megan, the deployment and growth has been very, very slow because, first of all, there's a learning curve. It's fundamentally different from IPv4. There's an investment involved in actually configuring, setting up, training people on it. And then there's also security considerations. Although it is, no protocol is 100% secure, but also IPv4 has been battle hardened. IPv6 is still being also, security issues are also being discovered, but they are not as serious as one may think them to be. But so these have been some of the obstacles that have slowed down the development and also deployment of IPv6. However, as I talk right now, the major service providers that you come to rely on for your daily internet needs, most of them support IPv6. And even in Kenya, I know some ISPs also support IPv6, and some actually are also rolling out. I'm not so sure if who is rolling out. Some perhaps also roll out to their customers. So in a way, it's going to take some time for it to fully get to the level that IPv4 came to, but all the same, there's progress being made in its deployment. I hope that answers or clarifies the difference between IPv6 and also the problems that actually that it faces in its deployment. All right, then. So the next one is AMRIT. Does ICANN assist with law enforcement efforts in investigating and prosecuting cybercrime? Yes, it does. My organization actually works with law enforcement in investigating mainly, not in law enforcement investigations when it comes to DNS abuse. So DNS abuse is actually any activity malicious. Sometimes it's intentional, but it's unintentional, but let's say malicious, any activity that basically affects or actually exploits or abuses the DNS, the domain name system, such as phishing, malware, domain names. And so from time to time, ICANN works in assisting law enforcement in actually investigating these malicious domains and also providing reports on abuse on the DNS. So ICANN has a program that's open to top-level domains and CCTLDs, which is known as the DNS abuse activity reporting called DAR. I'll share the links after this. After I've answered the questions. So DAR is actually open to top-level domains and even country code top-level domains. And also some of the reports are also shared with also entities such as Interpol on investigating what domains are actually being abused and also statistics on what is happening on the DNS on the DNS space with respect to security and abuse. So I hope that answers question, Amrit. All right, Faida, what measures does ICANN taken to ensure the internet users are safe when using the internet? Okay, so Faida, I want to just demystify something. ICANN doesn't control the internet. Our remit is quite limited. We only deal with the DNS, which is the yellow book or the phone directory of the internet. So when it comes to DNS, ICANN actually conducts various trainings on DNSSEC, which is the protocol for securing DNS. Like I mentioned earlier on, the internet was not built with security in mind. Even DNS itself was not actually built with security in mind. So in the late 90s as well, and there were activities to improve on the security of the DNS. And one of those initiatives was the standardization of a protocol known as the DNS security extensions, known as DNSSEC. So ICANN actually conducts trainings and actually sensitizes many stakeholders on implementing and deploying DNSSEC. And apart from that, ICANN also has the activities and initiatives such as the DAR, the DNS abuse activity reporting. We also have within what you call the Internet Identified Technology Health Indicators, ITHI. I'll send you all these links, which measures basically the health, or can I say, of various, let's just call it identifiers such as domain names, protocols, and whether they are susceptible to abuse or even or security breaches or so on. And then another project that is now being done by the ICANN community is DNS security facilitation initiative, which is actually now an ICANN community group. And so this one here is actually headed by our CEO, Yoran Mabi. In it, he wants the ICANN community to investigate and also look at the threat and also intelligence on the DNS system as a whole, and also make recommendations to the board. So basically, ICANN has several initiatives within the organization itself and among stakeholders for which it helps to improve the security of the DNS. I hope that answers your question. All right, Abdi Rahman, kindly comment briefly on the virtual office, what this portends for employers and employers as well as in the learning in all the view of the country, internet level preparedness. Abdi Rahman, I'm not sure what you mean by virtual office. Would you like to clarify?
Uh, Thank you so much. I was just asking for your thoughts on the, with the pandemic now, we have been thrust into a different environment, and the internet is playing a critical role in terms of business continuity. So that's what I meant in terms of the virtual office, and closely linked with it in terms of how, as a country, we are doing in terms of internet level preparedness. Because we're in Nairobi, and I think Nairobi, I wanted to get a picture of how we are doing at a country level. It's just a general comment if maybe you have some idea. Thank you.
Oh, okay. So I again, I'm not competent to describe this because I am not, I don't have the authority first and foremost, and also it is maybe outside also my remit as an ICANN employee. Maybe this one could be more directed towards perhaps the policymakers, perhaps who are in this chat, or even the government participants who are also on the chart. They could maybe give you a far better picture on maybe the country preparedness on when it comes to actually taking the office and taking everything online. All right, so let me see that. Okay, I just hope that answers your question, Abdi Rahman.
Yeah, thank you.
Okay, you're welcome. Vivian, what are some of the issues that are categorized as domain abuse? So, Vivian, I'm in a KICTAnet panel discussion that happened in September. I gave a list of activities that can constitute as domain abuse. One of them is phishing, which is basically sending, where actually a masquerade as an entity that is that is maybe a legitimate entity in order to attain maybe certain credentials, or for you to get data from for me to actually solicit data from you. So phishing is one of them. The other one is malware itself. So actually the fact that you have malware that is being spread by botnets, which actually are under the control of maybe an entity known as a bot master, using certain domain names. So usually these domain names are generated using a domain generation algorithm. This actually still constitutes as domain abuse because you're actually distributing malware using domain names that are generated by a botnet or bot master. The other one, basically, I would also put also threats to the DNS infrastructure. For example, a man in the middle attack. The fact that maybe when I send a DNS query to the ISP, there's somebody else who is actually listening in and determining what kind of domain or what kind of website or what kind of address I'm trying to actually access. So that one can also be constituted as that. When we actually also see that between the ISP and those servers, like the root server, like the authoritative servers, when there are certain also attacks that can actually hit that part of the infrastructure. So these are just some of the examples of domain name abuse, which is overt, as maybe in the sense of phishing, or even can also be very covert, like in the man in the middle attack. So these are just a few examples. Yeah. Okay. Well, Wambua, I may not be in a position to comment on the one as a solution for less connected areas. Again, this is outside my remit as ICANN. I just wanted to give an overview of the internet from the past to where we are and to the future. So I may not be able to comment about the LORA one. Okay. All right. Okay, thank you so much, Megan, for actually clarifying on the multi-stakeholder model of internet governance and also on the decentralization. And thank you also for your questions. All right, are there any more questions?
I have a question.
Okay.
Thank you for your presentation. We've been trying to follow up, and maybe you can shed some more light on who one can classify as an internet user. So when you speak of 4 billion internet users as at yesterday, do you mean human users or internet bots? Because sometimes you need to find who's liable for privacy or data breaches. So would you please shed some more light on what or who you'd classify as an internet user?
Okay.
Thank you.
So according to the ITF, and also various other definitions I've come across, internet users broadly describes human beings and also end user devices, not bots. So let's say like have a computer on online, and that one can also be classified as a user if it's maybe maybe it's sending an automated email like a reminder. But when you talk of bots, those are now software programs that actually perform certain tasks. Some may be malicious, some of it may be benign. So we don't classify bots as internet users. We're talking of actual physical devices, and we're talking of also human beings. But from the statistics I'm giving you, those ones are, to be clear, those are actually describing human users or human beings who actually are able to access the internet. So there are many matrices for measuring this from each of the various 98,000 networks. And there are ways to actually filter which ones are actually devices that are actually making noise, and which ones are actually from actual human beings. Maybe there are certain patterns. There are various algorithms for doing this. So we are talking that right now that more than half the planet is connected. That is, human users are connected to the internet. IoT is treated as a separate category because we are now talking of sensors and multiple smaller devices, which are increasingly becoming more and more common. And this ones will bring about more and more billions and billions and billions of devices now will actually be connecting online. And I give an example that it's projected that by 2025, we'll have more than 20 billion IoT devices that are now going to be on the internet. So I hope that clarifies the definition of internet users.
Yes, it does. Thank you.
Okay, then. If there are no further questions, I would like to hand the session back to Liz.
Probably a question before you, Paul.
Okay.
Yeah, thank you so much. So I was listening, and then on the issue of the domain name and the numbers. So are there country-specific sort of statistics if somebody was to follow these? And where can somebody be able to get this information?
Okay, so statistics on the total domain names, on country level domain name.
Yeah, and how they have been growing over time.
Yeah, all right. There are various statistics. I will pull some of them out from APNIC. I'll share with you after I'm actually concluded with this chat. So stick around on the chat. I'm going to share some resources. So yes, there are various statistics on domain names, on country code, top level domain names, top level domain names. I will actually share with you after the chat.
Thank you so much.
Okay, then back to you, Liz.
Thank you, Paul. Now I think we are done for the day. I'll only ask you to go through the self-learning platform so that we are ready for tomorrow's exercise, where I think we'll start by discussing module 1 and 2 still through the platform. If Caris is there, you can give us more instruction on this. If not, then we can just close for the day. Caris, take 1, take 2, take 3. Okay, sawa. Asanteni sana. I have just shared a WhatsApp group link for you guys to join. We've had a few glitches on communication on this, and I think WhatsApp will serve an easier platform for us to give you more communication about the platform and what is also expected of you. And also, if you need any contacts from our presenters, you can also ask from that platform. I've just posted it again. Feel free to join. We'll also, it's not like, it doesn't mean that you are going to abandon the other channels of communication, but I think it will supplement for you to get any urgent communication, maybe about your SATs, what names you prefer, or how you should receive your bundles. Okay, sawa sawa. Asanteni. I declare this session closed. Well, look. That is what I suggested. If, well, okay, I knew it. Oh.
Hi, Liz. Hello.
Hello.
My question is, when are the assignments for today due?
Sorry, I lost you.
When are the assignments for today due?
I think they are due today. That's why we have the afternoon session off.
Okay, thank you.
Yeah.
to understand that all things are only about yourself.